A query like seacrh is one human typo, but two Levenshtein edits. Damerau-Levenshtein scores the transposition correctly, so correction candidates rank the way users expect. You'll implement a Damerau-Levenshtein query corrector that ranks candidates and returns the correction, so an adjacent swap costs one edit. I'm Professor Pi, teaching search and IR with simple Python. Typos are everywhere in search. People swap neighbors, fat finger keys, or drop letters. A plain Levenshtein distance treats an adjacent swap as two edits, so reasonable fixes like seacrh can lose to less likely strings. Damerau-Levenshtein adds a transposition move and treats an adjacent swap as one edit. That usually makes corrections feel more human and surfaces the right candidate. Think of this as a compact piece of a query pipeline. You still do tokenization, stop words, and ranking. But a cheap spell corrector sits in front when a query returns few results or poor clicks. With a small vocabulary and an inexpensive distance function, you can correct queries in real time and recover many otherwise lost searches. In practice, that cuts zero-result queries and boosts click-through if you combine distance with term frequency. Intuitively, the goal is to notice that the letters are present but swapped. Humans see that immediately. Damerau-Levenshtein adds a swap operation to the usual insert, delete, and substitute moves, which is exactly what short, noisy queries need most. We'll build a tiny, focused pipeline, so the idea is obvious before you scale it. First, we'll isolate a swap, then compute plain Levenshtein, then add the transposition rule, and finally rank a few candidates by distance and frequency. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We first show the simple swap that a human would do to make the problem concrete. This snippet isolates the typo as one adjacent swap from seacrh to search. Before we talk about dynamic programming, the viewer needs to see the mismatch in the same way a human does. The letters are all present, but C and R are reversed. The slice expression builds fixed by keeping the prefix, swapping the two neighboring characters, and then keeping the suffix. That gives us a tiny reference case for the rest of the tutorial. The visible output shows the original query and the one-swap repair, which anchors the correction problem. Now we need a baseline distance to compare against, so we compute plain Levenshtein. This example computes the plain Levenshtein cost for the same query pair. The problem is that Lev only knows insertions, deletions, and substitutions, so an adjacent swap has to be explained indirectly. The rolling prev and row arrays are the standard dynamic programming frontier. Each cell chooses the cheapest delete, insert, or substitute path. For query and want, that means C to R and R to C are counted separately. The visible output shows a cost of 2, which explains why a swap typo can look worse than it should. That gap is what we must bridge, so we add the adjacent transposition rule to the recurrence. This code adds the missing operation, an adjacent transposition. The first three options in ops are still delete, insert, and substitute, matching the Lev recurrence from the previous step. The extra if checks whether the current two characters cross-match the previous two characters in the other string. When they do, damLev can jump back 2 positions through prev2 and pay 1 edit for the swap. This compact recurrence is aimed at adjacent transposed typos, which is the common query correction case here. The visible output drops the cost to 1, matching the human intuition. With distances in hand, it helps to translate numbers into an edit story so we can explain rankings. This snippet turns the distance difference into a concrete edit story. The next expression finds the position where one adjacent swap converts query into want. So the path labels come from the actual strings on screen. LevPath shows how plain Levenshtein must describe the same typo as two substitutions. Damerau shows the shorter explanation. Swap the neighboring seacrh pair. This is not a full backtrace visualizer. It is a focused path comparison for the transposed typo we are teaching. The visible output shows why the Damerau-style operation is the better correction signal. Finally, we use the distance to rank candidates and pick the best correction. This example finishes the mini baseline by ranking possible corrections. The terms dictionary stands in for a small vocabulary with simple frequency counts, which a real search system would usually estimate from logs or an index. Sorted uses dam-lev, query, t, first, so adjacent transpositions receive the correct one edit cost. The negative frequency term is only a tiebreaker, helping common terms win when edit distances match. That keeps the ranking rule simple enough to inspect, while still looking like an IR correction feature. The visible output selects search with edit cost 1, which is the intended correction. You can map this toy flow to a real system by replacing the small terms dictionary with a term frequency table from your query logs, and by limiting candidate generation to strings within a small edit radius for speed. 3 short points. Damerau-Levenshtein is Levenshtein plus an adjacent transposition move, so it treats common swaps as one edit. Use it when your queries are short and keyboard-induced swaps are common, or when you want human-like corrections. Remember that it targets adjacent swaps only. Broader transpositions or phonetic errors need other signals. A practical next step is to tune your candidate expansion radius. Measure top 1 correction accuracy while increasing the maximum edit distance from 1 to 2, and compare latency and false positive rate on a held-out query log. That single knob usually shows whether you need a wider net or better candidate filtering. If short practical IR helps, subscribe and watch the IR videos.